So in this lecture, we're going to be talking about bivariate correlations, specifically both the statistical technique and what it can and cannot show us in the data, some of the issues, and the bigger issues that we want to keep in mind as we're focused on statistical techniques. So whenever we talk about statistical techniques, we're actually talking about the mathematical equations that we're using to basically be more confident that the relationships that we have found in our data actually reflect the reality of what's actually going on in that data. Now, a couple of things that we need to remember is that this is a part of a larger picture of good research. So good research can't have bad statistics, but you could have great statistics and still not have necessarily good research. So kind of keep that in mind as we go forward, that though it is an important part, and we can't actually have a study unless we have that mathematical, statistical analysis that says there's a relationship going on, there's a lot more to research than just the statistics. So let's talk about first the statistics themselves, and then we're going to talk about their position in the bigger picture of research. So when we talk about bivariate correlations, we're talking about a specific statistical technique, specifically the bivariate correlation. Now, bivariate means bi is two, variate is variable. So this means it's a two variable correlation. It's one of the simpler statistical techniques that we can use. Now, that basically tells us if we have more than two variables, we're not going to be able to run a bivariate correlation. Also, correlations are somewhat limited in what they can actually look at. Correlations are specifically designed to look at one of two scenarios. The first one is that you have two variables and they're both quantitative continuous. So quantitative means they're numerical, and continuous means those numbers have meaning. Think about the various scales we talked about previously. We're talking about an interval or a ratio scale. So we have two variables that are either interval or ratio. In other words, the numbers have direction and there is approximately equal space between each variable. So whenever we're talking about a lot of psychological variables that are measured on a 1 to 4 scale, a 1 to 5 scale, a 1 to 7 scale, that's the kind of variables we're talking about for bivariate correlations. There is one other situation that can we use a bivariate correlation in, and that is that we have a single variable that is continuous. So again, it's that interval or ratio scale. And we have a second variable that's categorical, but with only two levels. So again, think of bivariate, bivariate. So we have two variables. One of them can be continuous, or both of them can be continuous, or one of them can be continuous, and the other one can be categorical, but only if it is also bi. It has two levels. So bivariate correlations simply give us a measurement of the association between the two measured variables. And the way we can review these associations is scatter plots if they're both continuous, or a bar graph if one of them is categorical with two levels. Whenever we get a correlation coefficient, it's going to be between +1 and -1. And this is another important part of correlations to understand. The sign, negative and positive, does not refer to the strength. It simply refers to the direction. So if you get a negative correlation, that means that as one variable increased, the other one decreased. If you get a positive correlation, that means as one variable increased, the other one increased. So we basically have either both are increasing or both are decreasing. That's a positive correlation. Or as one increases, the other decreases, or vice versa. That's a negative. The number is the actual strength of the correlation. So a correlation of 0 means there's no relationship whatsoever. A correlation of +1 or -1 would mean there's 100% correlation. There is no variance occurring. It is, as one increases, exactly the same increase is found in the other variable. We're going to dig into this a little bit more, but that's the biggest things to kind of remember when we're talking about correlations, is the correlation coefficient, which is usually represented statistically as an italicized lowercase r, is going to be between +1 and -1. The size of the number is the strength of the relationship, and the positive or negative sign is simply telling us the direction of the relationship. So again, when we're describing an association between two quantitative variables, we're going to use a scalar plot. We're basically going to create a variable, a visual representation of those variables, and each dot represents a single person's score on both variables. So for example, to the left there, we have percentage of deep talk between 0 and 100, and we have well-being scale. Now these are z-scores, so they go from negative to positive, but basically that just is a conversion to a different type of scale. All that you need to know there is that it is continuous. The difference between -2 and -1.5 is the same as the difference between 0.5 positive and 1.5. So each 0.5 increase or decrease is giving us the same information. We then basically start plotting points. So for example, one of the points up there at the top, percentage of deep talk 90, has got a -1 on the well-being scale. So that is that top left dot, if you will, on the chart. Once we have all of these charted, we can then put what's called a line of best fit. The line of best fit is basically a mathematical estimation of what is the strength of that relationship. The thing to know about, again, this is that if it's a straight line, in other words, there's no slope, that's generally going to be as an R of 0, so no correlation. If it slopes upwards, that's generally a positive relationship. If it slopes downwards, that's going to be a negative relationship. And the steeper it slopes, the tighter those points are to that line, we're starting to talk about a stronger relationship. The other way we can graph this visibly is if we're describing the association with categorical data and a quantitative data. So example, marital satisfaction, which is our quantitative variable. So again, it goes from 4 to 7. And then did you meet your spouse online or offline? And we can look at basically the means there. So generally speaking, according to this graph, people that actually met their spouses online have a 5.5 marital satisfaction, while those offline is probably 5.25. So there is a difference. So both of these give us an idea of what's going on in the data. What they don't tell us is how reliable that difference is, and we're going to talk about that as well. So just a quick reminder, measured variables, not any particular statistic, makes a study correlational. So what determines whether a study is a correlational study is simply how the variables were measured. If it's a bivariate correlation, that means that we have two variables, and either both of them are quantitative, or one of them is quantitative and one of them is categorical with two levels. That's simply telling us what the actual study is. As far as a study being correlational, when we talk about correlational studies, we're basically saying it's not a causal study. So remember that bivariate correlation is the name of a particular statistic. A correlational study is one that simply found relationships. A causal study is one that actually found causation. And remember again that if we're talking about causation, we need not just a statistical relationship, we also need to establish temporal precedence, that our cause preceded our effect, and that we need to rule out any other additional variables that could have been the cause. If we're talking about a correlational study, that simply means we found a relationship. We're not making a claim that one came before the other. So for example, we can talk about alcohol consumption and GPA. We could find a strong relationship. The more alcohol you consume, actually negative, the less your GPA, the less alcohol you consume, the better your GPA. But what we don't know is, does alcohol consumption cause poor GPA, or does poor GPA result in greater alcohol consumption? Now, we could have some hypotheses about what's going on there, but the study itself isn't telling us what's coming first. So let's take a couple looks at just some examples here of correlational data. So in this case, we're actually looking at correlational data that is two quantitative variables. So in other words, both of these are continuous. We have a Stroop score. In other words, the seconds it took to complete a task. So the more seconds is, the harder it was that task was. So someone that completed it in 80 seconds was better than someone who completed it in 150 seconds. We then asked people how many calories they ate at lunch. So again, we have a variance between 200 calories, a small stack or a protein bar, and 750 calories, probably a full meal. So a researcher invited a sample of college students to a lab at 1 p.m. to take an additional control test called the Stroop, in which color names are presented in different colors. After finishing the Stroop test, each student wrote down what foods he had consumed in the previous hour. And the researchers found out how many calories each student had eaten based on this information. Make a scatter plot of the data of the table below. What kind of association is this? Positive, negative, or zero? And does the association seem strong or weak? And do you notice any outliers? So I would suggest you actually hit pause and do this yourself. It's not a bad idea to graph this out. So go ahead and create a graph where on one axis, the Stroop test, that up and down axis, varies between 60 and 150. And then create the horizontal axis at the bottom with calories at lunch varying from 200 to about 750, and then basically plot each person's approximate position. And take a look at that scatter plot. So I'm going to give you a second to do that, so please pause. Coming back, here's what I came up with. So we can see the association between calories and Stroop. In other words, the less calories, the quicker people were at the Stroop test. Now, notice this is a negative correlation. As one variable goes up, the other one actually goes down, and vice versa. Now, what that does mean, though, is that we do need to know how things were coded. So remember that more seconds in here is worse performance, while more calories is a greater consumption of food. So again, we're taking a look at that Stroop score. The person that scored 150 actually had the least calories. So basically, less calories means poorer performance, because a Stroop score of 150 meant it took longer to do the task. When we look at people that completed the Stroop test very quickly, we see that they had larger meals. In other words, someone that had a large lunch actually tended to do better on this test. Now, this is fake data. This isn't actually necessarily saying that calorie consumption directly affects the Stroop score. This is just being used for an example. In this case, we do the same study, this time at 12 p.m., and we're simply asking people whether they had lunch or not, yes or no. So again, I would ask you to pause for a second and create the bar graph yourself. Figure out what the mean of everyone that said yes is. In other words, add 80 plus 90 plus 100 plus 80 plus 60 and divide by the number of yeses, which in this case is 5. Then calculate the no's. Add 120, 110, 120, and 130, and then divide by the number of no's. In this case, 1, 2, 3, 4. Get those two means and create the bar graph. So here's what I came up with once I did that. So again, what I find is that the people that said they didn't have lunch took longer on the Stroop test. They weren't as good. The people that said they did have a lunch scored better on that Stroop test. Now, again, I want to basically communicate that this is giving us a visual representation of the data. We can start to get an idea of what's going on. We can start getting an idea of the relationships, which is bigger, which is smaller, or what the relationship is as far as a positive or negative correlation. What this isn't giving us is some additional information that we definitely need to know when we're doing statistical analysis. So when we're interrogating association claims, so if we're reading someone that makes a claim of an association, we want to ask first construct validity. How well was each variable measured? And I'm going to give an example of this coming up, but basically we want to ask how were the variables actually measured, and do we agree that they were actually getting at what we're interested in? So for example, the Stroop test is basically a cognitive test of your ability to basically separate both the name and the color of a particular word. So for example, if green is presented in purple, you might be asked either what word is that or what color is that, and it goes back and forth. As far as the variable of lunch consumption, calories are basically based on memory. So we're not actually measuring how many calories we had. A potential better test might be that we actually give people a variance of calories. So they're asked not to eat before the study. They come in, the first thing they do is they consume a meal between 200 and 750 calories, and then we have them do the Stroop test. So again, how much do you believe that people are actually getting at what they're getting at in the study? Statistical validity is how well does the data support the conclusion. And we're going to talk about statistical validity, but again, I want to really stress that it's a small part of the issue. One of the concepts that often are talked about in methodology is garbage in, garbage out, which means that you can have great statistical validity, but if your construct validity is poor, in other words, you really didn't measure the variables you're measuring in, everything else doesn't really matter at that point. So our internal validity is, can we make a causal inference from that association? So remember, if we're making a causal claim, one causes the other, we need to control the order and we need to eliminate any other variables. Otherwise, it's not a causal claim, it's a correlational claim. We're finding a relationship, but we're not making that claim of causation. And finally, at the end of the study, we have to ask, to whom can this association be generalized? So the previous examples stated that it was college students, most likely in the United States, And they were also being tested either at lunchtime, 12 p.m., or an hour after lunchtime, 1 p.m. That also has cultural significance as well. So, who we could generalize, even if we had a strong construct validity, we believe the variables were measured well. We found data to support our conclusion. We even set it up in such a way that we could make a causal inference. In other words, we took control of the number of calories consumed prior to the Stroop test. The question then becomes, was there anything else that could be affecting this, and who can it be generalized to? So construct validity, just as a reminder, is how well each variable is measured, and was it measured reliably and with validity? In other words, would we find the same results every time? Are they actually correlating with other variables? And when we talk about construct validity, we're talking about a lot of different things that we want to look at. And I'm going to review that briefly on this next slide. So again, our variable one is where people met their spouse, online or offline. The second one is marital satisfaction for this particular example. And we can take a look at this. Operationalize. How well was the construct measured? That's the first thing that we'd ask. So where people met their spouse. Self-report answer to the question, did you meet your spouse online, yes or no? Do you think that actually gets at the construct of where you met your spouse? Especially for this particular study. Marital satisfaction is a self-report answer to 4-item couple satisfaction index. So there's 4 items. Each one indicates your degree of happiness of all things considered of your marriage, and in general, how satisfied are you with the marriage. Responses range from 1, extremely unhappy, to 7, feeling perfect. We then ask reliability questions. So test, retest. Do people give consistent answers to the question every time they take the survey? So for instance, if we did ask people multiple times if they met their spouse online, do we always get a yes or do we always get a no? Internal reliability is not relevant since this was a 1-item measure, and inter-rater reliability isn't relevant as basically we don't have multiple people doing an observation. When we look at marital satisfaction, do people give consistent answers to the CSI every time they take it? So again, that test, retest. As far as internal reliability, we can now ask, do the 4 items correlate with each other? In other words, is there a strong Combrax alpha for this particular test? And again, inter-rater reliability is not relevant as this is a self-report measure. It's not people watching the behavior. We then get to measurement validity questions, face validity and content validity. Does this item look like a good measure of where people met their spouse? Is it actually getting at that? Is it easily understood? And are people likely to respond positively and in a way that makes sense? For the marital satisfaction, do the CSI items look like a good way to ask about marital satisfaction? Is there other ways to ask? And do you believe this is actually getting at the construct of marital satisfaction? As far as criterion validity, do people's answers to the marital question correlate with where they met their spouse? For example, can the answers be collaborated with online membership records or dating sites? When we look at the marital satisfaction, do people's answers to the CSI items correlate with behaviors or outcomes related to marital satisfaction? In other words, do people that have a high CSI score also have lower divorce rates or a lower number of reported arguments? When we look at convergent validity, we're looking at, are there other measures that actually support this statistically? So looking at where people met their spouse, if there is more than one measure of where people met, do they correlate with each other? In other words, if we ask people a follow-up question about where they met their spouse, if they said they met them online, does the information from that second question also support this? For the CSI, do the CSI items correlate strongly with a second measure of marital satisfaction that was used in the same study? So in this example, there was actually 2 measures of marital satisfaction. One of them was 11-item chemistry measure, so how much chemistry you have with your partner. And in fact, it was highly correlated, an R of 0.78. Remember, the highest correlation we could find is an R of 1.0, so that's pretty decent. And finally, discriminant validity. Is the question about meeting people's online, offline really getting at where people met or something else, such as their ability to remember accurately? In other words, there's something else going on. And finally, with marital satisfaction, do the CSI items correlate more weakly with the similar measures, such as a people's agreeableness or their conscientiousness? We'd expect it to be strongly correlated with similar measures and less strongly correlated with less similar measures. So when we talk about statistical validity, we're actually talking about, again, we're just looking at the statistic itself. We're no longer concerned with that, how the constructs are made. So the first thing we want to ask is, what is the effect size? In other words, how strong is the relationship? So with correlation, that's going to be how close is that number to 1.0 or negative 1.0. The second thing we want to ask is the correlation statistically significant? Now, lay people that haven't had training in this, typically focus simply on statistical significance. In fact, you'll often see studies that claim this was found to be statistically significant, like that is the end all of what's going on. Statistical significance is actually just the starting point of statistical validity. All statistical significance reflects is the chance that you're wrong. So, for example, in the social sciences, it's generally accepted that a statistical significance of a p-value, that's basically a measure of statistical significance, of 0.05 or smaller is significant. What does that p-value represent? Well, the p-value represents the percentage chance that you're wrong. So if you have a 0.05, a 0.04, or a 0.03, that respectively means that you have a 5% chance of being wrong, 4% chance of being wrong, or a 3% chance of being wrong. So generally, though the reality is the stronger the effect size, the more likely a correlation is going to be statistically significant. However, simply referring to statistical significance as a proxy for effect size is not correct. And the reason for that is that statistical significance is strongly affected by the size of your sample. You have thousands of people in your study, you're going to find a much smaller effect size is actually statistically significant. If you've only got 10 people in your study, you're going to have to find a very large effect size for it to be statistically significant. And that's because statistical significance is simply determining, based on the data and based on the pattern you found, how big of an effect is necessary for you to be fairly certain that what you found is actually true. We then want to ask, could outliers be affecting the association? And we're going to talk about outliers a little bit more as this lecture continues. Is there a restriction of range? That's another thing we're going to talk about. And finally, is the association curvilinear? So basically, this is also the assumptions of a bivariate correlation. The last three especially. Bivariate correlations assume that you have looked for outliers and adjusted for them, often removing them. By the way, if you remove an outlier, you need to make that clear in your paper. You can't do that behind the scenes. You have to say, the following person was removed as an outlier in this data. You need to check to see if there's a restriction of range. Bivariate correlations assume that there is not a restriction of range. And finally, you need to make sure that the relationship actually is linear. In other words, the best answer to this data is to create a straight line through it, whether that line is flat, sloping upwards, or sloping downward. If the association is actually there but curvilinear, a bivariate correlation will not find that relationship. So generally speaking, the stronger the correlation, the stronger the effect size. Stronger effect size prevents more accurate predictions, and stronger effect sizes are typically more important. All else being equal, stronger effect sizes are more likely to be statistically significant. So again, we can take a look at this top one versus this bottom one. Notice that when we make the line of best fit in that top data, it is sloping positively. It's probably a positive correlation, but it's not as strong. The points are spread out. There's a lot of error going on there. In fact, there's only a couple of people that are actually on that line of best fit. If we look at the bottom example, we start to see a tightening of that data. One, the line is more sloped. As we get to a more sloping line, we're going to see a larger effect size. You're also going to notice that there's a fair amount more people along that line that are actually on the line, and those that aren't are closer to the line. So that would be an example of a stronger relationship. When we're looking at this, we're also using that line of best fit as our prediction line. In other words, if we were looking at someone else where we only had one of those two variables, we would be able to make a prediction of what their other variable would be based on this correlation. So for example, in here, we do actually have the example where Hugo is being predicted about the same in both cases. He's almost on the line of best fit. But in one case, the top one, we have a very strong correlation. In other words, there's not a lot of data or a lot of people, there's not a lot of variance between people either above or below that line. When we look at that second line of data, we're actually seeing a lot more variance. And taking a look at that, we can see that pretty much the strongest or the most error we find in the top one is probably about 10 points. If we actually look at the bottom, our error is about 40 or 50 points on the same scale. So stronger effect sizes prevent more accurate prediction. So the more likely, if something is statistic validity is how likely is it that what we found is actually important. That's different than statistical significance. Significance is simply a measure of how probable it is that we're correct if we're making a claim of an assumption. Statistical validity is how important is that assumption. So generally speaking, excuse me, all else being equal, the stronger effect sizes are more likely to be statistical significance. So we have a table here from a particular study, and what we're looking at actually is a whole bunch of bivariate correlations. So just looking at the top line interaction variable, whether someone was alone or not. We have the intercoder reliability, the well-being index, the satisfaction with life, the happiness, the correlation with well-being on weekdays, correlation with well-being on weekends, and correlation with well-being accounted for by personal differences. Now notice that if someone's alone, we're actually seeing a fair amount of negative correlations. And the stars are telling us that they are statistically significant. 2 stars usually means greater statistical significance, in this case a p of 0.01 or less. By the way, this is a good time to make the comment, we never report a p of 0. There's always a chance we're wrong. In fact, generally speaking in the social sciences, what you're going to find is the lowest p-value ever reported is going to be less than 0.001. So in this case, a single star means that we are 5% or smaller likely to be correct or incorrect. So for example, a p of 0.05 on a test basically refers to there's a 95% chance we're right and a 5% chance we're wrong. If it's less than 0.01, that means there's less than a 0.01% chance we're wrong and a 99+% chance we're right. And again, you can see as we look at these that if we look at ones with only a single star, we're seeing correlations of 26, 25. If we're looking at 2 stars, we're usually looking at 30s and above. So again, that kind of represents the fact the stronger the relationship, the more likely it is statistically significant. So again, let's take a look at some outliers here. So I did mention that we do want to look at outliers and decide what to do with them. So in the top example, we have both the top and the bottom. Notice that outlier is actually making a stronger relationship. It's dragging that line of best fit towards it. And the outlier in this case is that top right dot in the first left-hand series of columns, both top and bottom. In other words, with the outlier, our R is 0.37. It's a fairly strong relationship. But notice it's actually not doing a great job of predicting. The second one is an R of 0.26. In other words, it's not as strong as a relationship, but without that outlier, it's also a better line of prediction. So for example, if we look at the top one, we notice that almost all the scores are below that line of best fit. While at the bottom one, we basically have a near equal number of people above and below. Let's go ahead and take a look at the right one. And again, we have an outlier. With the outlier, our R is 0.49. Without the outlier, it's actually 0.15. And in this case, again, what you find is that though that outlier is giving you a stronger relationship, it is a much less representational relationship of what's going on. Outliers often have more impact when the sample is smaller. So the more and more people you have, the less and less influence an outlier has. We also talk about restriction of range, and this makes the sample correlation appear smaller than it really is in the population. So again, we have an example here where we're looking at a restriction of range basically means if I was for example, if I was interested in GPA and I took a study in an advanced calculus class where everyone's GPA was 3.75 or higher, that's going to be a restricted range. We're basically going to be able to say, well, if I find a relationship, that relationship only refers to a small number of students that all have high GPA. What I probably want, especially if my score is in general, is I want GPAs of everyone. So in other words, I want people from the highest to the lowest scores possible within that sample. So again, taking a look at this, if we actually looked at SAT scores, only those that had 180 or higher on their college GPA, I'd actually find a relatively weak relationship. But if I included people whose SAT scores were lower, I'd actually find a stronger relationship. Not a strong relationship, but a stronger relationship. And finally, we have curvilinear data. If the pattern of data is curvilinear, the R will be close to 0. If I tried to draw a line of best fit, it would be a relatively flat line, even though there is a strong relationship between these variables. So in this case, the R is 0.01, a value that does not adequately describe the relationship. In this case, we need a more advanced statistical technique to look for this relationship. And there are a fair amount of these relationships where basically you find a positive relationship at the top end of a scale and a negative relationship at the bottom end of the scale. And finally, we need to ask, can we make that internally valid causal inference? So again, we have to start, when we start with making a causal reference, we always start with covariance. We found a statistical relationship. There is a relationship between A and B. The next thing we need to do is methodological. Can we make an argument that we controlled A leading to B or B leading to A? If we can't, we have a correlational study. We're done. If you can, we then move on to the third step. Through our methodology, can we argue that there is no other possible explanation for why A resulted in B or B resulted in A? In other words, is there any plausible third variables that we cannot, and if there are, we can again not talk about causation. We'll talk about correlation. We have a strong belief that this preceded that, but we don't actually know if that was a causal relationship. Sometimes the third variable is an internal validity problem, sometimes it's not. The pattern of the data can help you understand this. So if a third variable, education, is an internal validity problem, we can take a look at basically plotting out how people's percentage of substance conversations, for example, in this case, we're looking at the far left table or scatter plot. We have percentage of substance conversations and well-being score. We can then actually ask the question, is education a problem with this? And what we can look at is people that have high scores on education and low scores and actually varying them out. If we find a relationship more like this one, we actually have a fair amount of information that education may be a major play in this factor. In other words, people with higher education have more substance conversations and score higher on the well-being scale. So education may be driving this difference, not what we've thought. If we do the same and we actually find that they're not as clear cut, they're more intermingled, there are some higher scores, there are some lower scores, but it's more of ovals than circles, this generally means that there was a relationship regardless of education. So when we find two distinct groups without a strong evidence of a correlation between the two of them, we have evidence that it is an internal validity problem. If we have two distinct groups based on a third variable, where we still find a similar pattern of relationship. So for example, if we look at that first table, if all I was looking at was the data from people with low education, the blue dots to the left, if I ran a line of correlation through that, I'd probably find no relationship. If I did it with people that had high education, and again, all I looked at was percentage of conversations and well-being, again, if I drew a line of best fit, it would probably be straight. The reality is that the relationship I found was based on education. In the one on the right, we actually find that if I actually look at it in isolation, so education low, the relationship between the two variables, education high, the relationship with the new variables, both of these relationships still show a correlation. There's still a positive correlation between the variables. This would be an indication that, yeah, education has an effect, but it doesn't actually directly alter the relationship. In other words, if you're low educated, you still have a positive relationship between your percentage of conversations and your well-being score. And if you have a high education, you still find a relationship between well-being and percentage of conversation score. So finally, we need to ask about external validity. How did they get their sample, and does external validity really matter in an association claim? So the first thing is mostly external validity is focused on how is the sample gathered and what conclusions are being drawn from the specific study to the broader population. And we've already kind of talked about sampling from population. We do have to recognize that external validity doesn't necessarily matter in an association claim. In other words, it doesn't affect our methods. It doesn't affect our results. What it does affect is, can we actually use that information to a broader population? So your assignment for Chapter 8 is pretty straightforward. You're going to be given an example, and you're going to be asked some questions. So what does a negative correlation mean in this example? Is this a relationship strong or weak? So the big things to remember here is the strength is the number. The sign, whether positive or negative, is simply the sign. And again, if it's negative, that means that as one variable went up, the other one went down. And again, it is important to know how these variables were coded. And if it was a positive relationship, it generally resulted with no sign whatsoever. So usually you'll see a negative correlation reported as negative 0.55. If it was a positive relationship, it'd probably be just reported as 0.55. But again, that positive relationship means as one variable goes up, the other one goes up as well. What does the p of less than 0.01 mean in this result? So remember what p represents. P is statistical significance, and it's simply a proportional chance that you're wrong. In this case, it's less than 0.01. There's a 99% chance that the relationship was in the data, that you're not making an assumption based on just random chance. C, what happens to this correlation if you added one person to the sample who drank much more beer than other students and had a much lower GPA? So you're going to be given an example of basically an outlier, and I want you to think about what that outlier would do to the data. And finally, Popular Press reported about this article was headline, Drinking Beer Decreases GPA. Is this causal claim justified? So again, within the example you're given, are you actually finding evidence within that claim that there's cause? In this case, there would not be.